Okay. So in today's lecture, I'm going to continue to talk about training a neural network. This is a very important topics. There are a lot of like rule of thumb, and also some a little bit math theory in training the neural networks. So, so neural networks has a lot of parameters. If we do not process that properly, it's very likely you won't get the good results. So this is very important topics. Okay, so today, I think today we're going to focus on the first part, improve your training area, which you are going to get a good optimization, and a good optimizer, other than the stochastic gradient descent and the mini batch gradient descent. So these are the two things that we talk about. The second thing I'm going to talk about is the learning rate schedules. So, like today, I'm going to focus on this. I don't think we can focus and finish all slides here. I might leave the improve your test area into the last lectures. Okay, so there are other optimizers other than SGD. So so we talk about gradient descent, right? So I mean the optimization, the whole thing is basically two steps. The first step is we find out the gradient. Then we just update the parameter. So this is like exact the vanilla gradient descent. So we calculate the exact gradient, then we update the parameter with the step size that preset, like step size. All right, so but we know this is not efficient because the first thing is evaluate this gradient could be very, very expensive because you have tons of data. To calculate this, I mean, weight and the gradient could take forever. So that's why you are going to take really, really long time to get one step update of the weight. So that's not efficient at all. So that's why we do stochastic gradient descent. So instead of you take the full batch gradient, you just feed one by one to use the like individual gradient to do the update. So theoretically, I mean, it will be slower, but in practice, it will be faster just because we are and updating the weight more often. But there are other issues in stochastic gradient descent, particularly if we have a pretty bad loss functions. So for example, this is the problem. If the loss change quickly in one direction and slowly in the other, so what will happen do? So like for example, in this direction, the loss change quickly, but on the other hand, in this directions, the loss change slowly. So this is the loss condition, and the loss function has a very high condition numbers. So that means the ratio of the largest to smallest singular values is very large. So that means some singular value could be like super small, some singular values could be super large. So as a result, this will be very hard to optimize. So if we actually have that kind of the problem, and use SGD, actually you will get some very slow progress along this like shadow direction. So like basically in this like change quickly in one direction, it will move really, really fast. So because you are going to calculate this delta t, and they will overshoot, then coming back, overshoot, coming back. So this will jitter along the steep directions. We know eventually it will converge, but this will very, very slow. So the progress will very slow along, this shallow dimension. So this is an intrinsic problem in stochastic gradient descent. Like particularly if you have a very high condition numbers, you will see the large oscillations around around the values. Okay, so so this is the problem one. The problem two is in stochastic gradient descent. Like particularly if you're using mini batch gradient descent, if we have a local minimum and or a saddle point like that, it actually has zero gradient, the normal gradient descent will get stuck. If you're using stochastic gradient descent, it will bouncing around, right? So it will basically bouncing around, these regions. It will be hard to like overcome the barrier between this and this to go over this landscape here. Okay, so we know somewhere here should have smaller loss functions, but this optimizer doesn't know it. Okay, so and also this kind of saddle point is very common in high dimensions, just because say if we have like 10,000 dimensions, which is very common in AI applications, it's possible 999,000 and dimensions are like local and minimal. There are a few others actually is being local maximal. So that's why, if you do random search, in most directions that you searched will be local minimal, but only very little dimensions that you search actually give you the local maximum. So that's why you are like run into the saddle point. But the issue is, how do I know which direction should I go? So this is a very tricky question. Saddle point, it's very, there's a myth in like training that like neural network, why they get stuck somewhere. There are general consensus is just, they might stuck in the saddle point rather than the local minimum. Okay. There's another problem in stochastic gradient descent is because our gradient is coming from mini batches, so this could be very noisy. So that's why if you do zigzag, so it will be like it might like and going up, going down. It'll be very, very zigzag. It will be very, very noisy. Okay, okay, so this is something that it's not the main issue here. But we can make our batches slightly bigger, so it will be less noisy. So what we can do is actually we can add some momentum. So think about think about the ball like rolling along the hills. If we don't have the velocity, think about the ball actually. A hill. This landscape is actually putting the honey. Then this ball rolls very, very slowly. And then there's like the velocity, will be like dragged by the resistance. Then it will get stuck in this like local minimums. It will not be easily and explore for the and for the area, because it will be hard to overcome this hill. On the other hand, if you have velocity, you have momentum. If you start the ball right here, it will go over and there will be momentum to climb up, then to further explore the other territories. So this momentum actually is very important, because if you have some region that has little like hill and gap, this momentum can take you out this local minimum and get into some other places. And also the saddle point here, right? So if you have a local and momentum, this momentum can push you away to this and the saddle point. Okay, so this is very important. So if you have very poor condition, if you're using stochastic gradient descent, you are going doing zigzag. If you do have the momentum, it will be correctly and identify where they should go. So for stochastic gradient descent, this is a very simple two-line update of code, right? So basically, you have a gradient, then you update your weight. So this is similar as vanilla and the gradient descent, very simple two-line update code. So this is why we use that, and it's very useful and effective. But as time goes on, and we find and they also have a lot of limitations. So that's why we want to try and get other versions of things to work out, and other like different optimizers. So this is stochastic gradient descent plus momentum. So that means we are continue moving in the general directions as the previous iteration. So it carries out not only the axis, we also have the velocity will be carried out. So that's why we are going to build up the velocity as the running mean of the gradient. So we're going to keep track of the previous gradient, and this will be a very important like informations to help us to overcome those saddle point and other local minimums. So what we actually do is very simple. So we keep track of the gradient informations. We damp the previous like velocity and at this current and a gradient. So this will be my velocity here. So this velocity is actually have the information of the previous gradient. So like you can think about this as running average of the previous gradient. As once we have this information, instead of we like directly and update along the gradient information, we actually and update with the velocity informations, right? So this is a very important and the methods actually being used and proposed like 12 years ago. So like super popular right now with a stochastic gradient descent plus momentum. Okay, so these efficiency right here is usually set as like 0.9 or 0.99. So these values are actually just preset, right? So this is basically we are saying we want to forget those old like gradient, but I want to forget those old gradient gradually at the rate of 0.9 or 0.99. So this is basically says I'm going to take a running mean, but I want to emphasize more with the latest gradients. Okay. All right, so the code is still very simple. So you basically initialize the velocity here, then you compute a gradient, then you compute like an iterative ways of the velocity, then you update your x with the velocities, right? Just 4 lines of code. So you actually need to implement that in the homework for the stochastic gradient descent plus the momentum. Okay, so all right, so yeah, this is and they also have like so alternative equivalent formulations. So this is the formulations we use here, but we can use the other one. So like and here and we can move this alpha and back into top right here. Then basically says we can actually like and get like minus alpha on the top. So basically if we like multiply the minus alpha on the both hand side, you will get something like this, right? So this is basically the exact same and equivalent formulations, and of course in this cases the mu will be the rho will be different, right? So the rho will be minus alpha in this formulations. It just like you have a different formulations and different ways to accumulate these weights. All right, so wait, I think it's the same rho. Am I right? Yeah. Sorry, I was wrong here. I think think about because my v here is start with a 0, so that's why so that would be the same rho here. And you can use the same rho so as it before. So if you follow the iterative schemes, and you will find the whole thing, it will be exact the same thing. Yes. So this formulation is correct that the rho will be the same rho 0.9 or 0.99. So this will give you, so basically the same formulation. They are equivalent, just different ways to formulate things. Okay, so that's why, like kind of in practice, people use this kind of formulation a little bit more, I think. So, why this is important? Is is you think about, here we have two vectors. One is the x of t, another vector is like vt plus one. So like basically you have two vectors and you basically add these two vectors together. So this is actually, and also the momentum and update is basically we have the velocities and also the gradient, right? So you have, and the velocity, and you shrink the velocity and the previous velocity and a little bit, then you add another gradient and informations. So you have the like velocity and a gradient. So this is the actual and the step you are going to and apply. So this is, actually combine the gradient at the current point with the velocity to get step used to update the weights. There are other ways that we can use. That means, so I'm going to show you what is that. So the formula first. So this is called like an Nestrov and momentum. So I want to remind you previously we have xt here, but you can x and say, okay, I'm going to use the xt plus rho vt, which is the predicted future point, as a better an approximation for my and for my gradient. Because if we just take xt plus rho vt, so this is a bit like we are taking the future point. We hope the future point has a better information than the current point. So that's why this is called Nestrov and the momentum. So actually, if like for this point right here, so we hope this has a better and a better gradient informations than xt itself. But so that's why what we are doing here, we are not taking the current gradient. We are looking ahead to the point and we're updating using velocity will take us. So this is the gradient that using hypothetically the future point of and a gradient of the future point, hopefully we can get a better result. So update and compute a gradient there and mix with the velocity to get actual and update direction. So this is not the gradient of the current point. It's actually the point that we look ahead using, and we using hypothetically the future point, the gradient information. Okay, so right here, so this is the natural of like momentum. But if we write everything in this way, this is quite annoying. So because I want everything to and our update to be xt and a gradient of fxt. So this way we can compute everything very easily and nicely. But if you want me to compute something that like I'm xt plus rho vt, this whole update schemes will be a little bit like annoying and computationally will be inefficient. So what we usually do here is we are going to change the variables with x2 being defined xt plus and plus rho vt. So then we are going to rearrange the orders. So if we have followed this definitions, so this thing right here will be substituted by the x2t, and right here, so we have x2 t plus 1 and x2. And right here we have, if we minus rho vt, so this term will becomes xt, and this right here becomes so we know we're going to add the add vt plus 1, and also we need to add the rho vt plus 1 to ensure we get x2. So like this is basically we subtract rho VT and add the rho VT plus 1 to ensure our definition to be correct. So as a result, we're getting these formulations here, right? So this is called, and this is, I'm actually called the, like Nash-Rov and the momentum method. And of course, I mean, so eventually it doesn't matter how you choose the X2 to start with, and you can always choose some random initial point to be your X2, and then you follow the exact schemes to update. Okay. All right, so that's good. And in addition, there will be something called an ADA grad. So this is some other methods really being and discussed in almost 14 years ago. It's called, it's basically called adaptive gradient. So one of the things that we encountered, and the problem is, in some direction, the gradient is super large. In some directions, the gradient is super small, right? So, and in each component. So that's why we have a problem. That problem caused the issue of the, like, so the condition of hashing number is really large. So in light of this idea, so what we can think about is, can we just keep track about those values of the gradient informations? If my gradient in that component is really, really large, I'm going to divide this very large number, right? So to make sure they are in the controlled and the regions. If my gradient information on that component is really, really small, then I'm going to divide by that number, and hopefully my gradient will be getting bigger to that component. So this is called adaptive gradient informations. So this actually adds an element-wise scaling of the gradient based on the history sum of square in each component. So you have a component, you have a very long and gradient and large gradient informations for each component. So you are going to add this element-wise scaling of the gradient based on historic sum. If certain component always consistently give you very small gradient, you are going to divide by the square root of the square gradient to ensure you can enlarge this gradient informations. And historically speaking, if the gradient is really, really large and in that component, you are going to divide by and the square of the sum of the gradient, so you can make sure your gradient to be small. So this is called per parameter learning rate and adaptive learning rate. Sorry, so this is very important. And also I want to emphasize this dx times dx, they are element-wise product. Okay, so they are not taking any inner product here, okay? We are not taking inner product of the gradient. We are taking the element-wise product here. Okay, so so that's why if we, and of course we need to add some like 10 to the minus 7 to ensure this whole thing doesn't go to like 0, right? So if this thing goes to 0, we have a little bit issue here. And obviously it will blow up. So this for the ADA and grad, in the very steep directions, I'm going to make my learning rate is to be smaller. But in the flat direction, it will be accelerated, right? Because in the flat directions, my gradient is always very small, and I'm going to basically amplify it by and so I intentionally amplify this so gradient. But if my gradient value is really large in steep directions, then the gradient value will be shrinked. So like by that amount, such that in each directions, I want my gradient to have the similar scales. Okay, so this is very important. So this is the idea, an idea of adaptive and a gradient, and the learning rate. So that's why you have this kind of if you do that, you will not get zigzags. You actually will get a smooth transition to the local minimums. Okay, so this is very, very useful if you have, if you believe certain gradient has very large value and a certain gradient has very small values. Okay, so another issue is if we, if we do that, so this like step size is always divided by square root of sum of squares of the past gradient informations, and of course the gradient is getting bigger and bigger, and your learning rate is getting smaller and smaller, which is step size is getting smaller and smaller. So basically, automatically you are doing the scheduling already. So this is also an issue here because if you really has a very large and the sum of the gradient and the sum of square gradient, this learning rate will decay very, very fast, right? So you don't want to do that sometimes because it might just not learn at all. So that's why, so you want to do something like leaky ADA grad. So that means not only you are doing this like an adaptive learning rate for each component, you also want to leak a little bit like gradient informations such that it has a two component. One is just purely gradient informations. Another one is just adaptive and the scaling here, right? So this is something that can give you some idea that like the things will not just purely goes away, right? So this is the leaky ADA grad idea, right? This is called like an IMS prompt. Okay, so now we are ready to introduce the Atom. So Atom optimization and optimizer is very, very very important. One of the most like popular, I would say the most popular and optimizer in deep learning. So, and you can see we talk about ADA grad, IMC prompt. This is basically the idea of we want to have rescale the component at each and introduce the component wise and the learning rate. But we can also add the momentum. So this whole idea is we have IMS prompt, but I'm going to add some momentum to that. So if we actually look this, so we have we basically have two momentum terms, right? So the first momentum term is just the momentum term we talk about in like SGD momentum. The second part is literally basically the RMS and IMS prompt, right? So this is like you have two contributions from the first momentum and the second momentum. Then you are going to adding some bias corrections because you adding some bias to that. So you actually need to do some bias corrections for the fact that the first and second momentum estimate will start to zero. So like if you don't do that, this actually will not start with the zero. Will actually start with and you scale with like 1 minus beta 1 and 1 minus beta 2 here, right? So that's why you need to do the scale and so you are going to keep multiplying the 1 minus beta 1 and 1 minus beta 2. So so that's why you need to correct this bias by multiplying this like 1 minus beta 1 power of t and 1 minus beta 2 of power of t. Okay. So this is something that you need to and keep track of. So this is bias correction. So okay, so you might ask, so why this is 1 divided by 1 minus beta 1 power of t? So this is like you so you need to like think about how you do it, right? So you have like 1 beta and 1 minus beta 1. You have and 1 minus beta 1 squared, 1 minus beta 1 like cube, and you sum them together, right? So that's why you and you want to divide that. I mean, that's the component you actually need to divide it and eventually to reduce the bias. Okay, so in Atom, you get beta 1 is 0.9, beta 2 is 0.999, and choose a very small learning rate, right? So that will be very good starting point for many models, right? So you need to actually and implement these atoms and from scratch. So I mean, it's not that hard. It's just 5-6 lines. Okay. And also, you can actually add L2 regularization if you need it. So this is also very popular at L2 regularization. I'm always L2 regularization is I mean a lot of cases will be a good thing. And also you can do the weight decay. So I mean, so in these cases, like L2 regularization and plus weight decay is actually exactly the same because I mean, if you add L2 regularization, this is like plus lambda of the square of the weight. If we take derivatives, this is basically 2 times lambda of WT, right? So this is basically we are doing the weight decays. So, but they are different in atoms and IM's prompt and ADA grad. It just because I mean the weight decay that we're doing here, it's different because we have more stuff, we have a momentum, we have other stuff, right? So there are more things that that we are doing, and also we basically in the IMS and prom and ADA grad, the gradient information is already being scaled, right? So and I amplify certain component and I suppress certain components. So that's why the weight decay is not an exact the same thing with the L2 regularizations. Right? So because we already changed the weight while we do the gradient descent. So this is like basically if we have like an adaptive methods, these two things will be different. All right, so there are like Adam W. I'm not going to get into this. It's more complicated. So basically, we are doing the like atom with L2 regularizations and atom with the decoupled weighted decay. So these two things we can still add them on, but it will be different. So because we so as I said, SGD momentum, they are the same. But for these kind of adaptive methods, it will be different. So we have to do it a little bit carefully. So, and Adam W. It's another popular one. Just the whole idea is just we are adding any regularization in the right ways to do so. Okay. Let me take a break. Okay, so that's all these fancy optimization, first order optimizations. So basically what we did is we only use first order information, that we use the gradient information to do optimizations. So so all these optimizations that we presented are first order optimizations. We use the gradient from the linear approximations and the step to minimize. Then we like use the gradient information to minimize the approximations. We could use second order optimization. That means we are not only using the gradient, we can also use the hashing to form the like quadratic approximations, that we have a step to the minimum of the approximations. So this is also a very popular way. So particularly if you can estimate hashing very efficiently, second order optimization is a very good and approaches. So the whole idea is of the second order optimization is basically the Newton's method. So what we do is we take the second order Taylor expansions of this high order approximation of the and the loss functions, and basically this is the zeroth order, this is first order, this is the second order. So what we do is we take this Newton's parameter update to solve this critical point. But here is we actually need to solve a very difficult linear system problems, which is H inverse times the gradient. The issue is the Hessian will have order of n squared elements. Inverting that will takes n cube, which is a very expensive and operations. So that's why this will be very bad for deep learning, and for obvious reason, this is not a very good idea. So that's why we want to do some like quasi-Newton. So one of the the thing is, instead of inverting this Hessian, which is take of order of n cube, we are going to approximate the inverse Hessians with the rank 1 update with only n squared and optimization. So this is called like an BFGS. The typo here should be BFGS, not BGFS. This is also a very popular methods, and also here we have a limited memories of BFGS if needed. Okay, and so for that, I'm actually this like an BF and GS actually works very well for the full batch. If you if your batch is not that big and everything is deterministic, it usually it still works very well. But that whole idea doesn't transfer very well to mini batch settings. Usually give a very bad end result. So adapting the second order method to large scale stochastic setting is a very active research area. So this whole idea is not fully explored. If you really want to use second order methods, you should use the full batch and the deterministic mode in these cases. So in general, I would say Adam W and Adam are both very popular choices. Here you say like probably your default optimizer for new problem. I would say probably I would choose Adam first, and I would choose Adam W. The second choice. But that's just my personal opinion. There are many other people who will choose Adam W first, then choose Adam in the second, right? So this is often works okay even with a constant learning rate. Okay, so this is something that just keep in mind. SGD with the momentum can actually outperform Adam, but may require a lot of tuning with the learning rate and schedule. So I'm going to talk about this like momentarily. So SGD and the momentum can do really good job if we know how to tune those schedules. Okay, so these are the take-home message for these optimizers. So this is it's extremely important topics. I'm actually in the homework you are going to implement several of the optimizers. Learning rate schedules. So these are also extremely important because this learning rate and tuning will make a huge make a huge differences with the performances. So we have SGD momentum, and ADA grad, IM's prop, and they all have like learning rate as the hyperparameters. And of course, as if you have very high learning rate, so your loss will not decay. You will actually go up because we overshoot. Um, if we have a very low learning rate, things will just converge really, really slow, right? So you can see this decay rate is really, really slow. If we have a high learning rate, it will drop into some level, but it will bouncing around. So that means it's like we remain a very high loss. So that's also a not very good job. A good learning rate is it can decay sufficient fast, and the final loss is will be lower enough, right? So there's a lot of tuning and experiences how to choose this learning rate. So, and of course, this red one will be the best learning rate to use. Um, but but in reality, how do we choose that? So the whole idea of the learning, you think about it, we are like rolling a ball down to the well. So initially, it would take very big like steps. It will rolling along the hill. So it's like rolling literally like along the hill. But in this case, it's our whale that it's the local minimum that we're trying to achieve. It's very steep, right? So that means if we take a constant learning rate, it will not jump into this well because we assume this like and distance will be will be constant. So that means it will likely to overshoot. Once we overshoot, it might bouncing around the well. So that's exactly what happened if we take very high learning rate. So it will not hit this local minimum. Rather, it will be bouncing around this well. So what we can do here is we can actually reduce the learning rate at a few fixed point. So this is being used in the ResNet. So that means we can multiply this learning rate by 0.1 after epoch 30, 60, and 90. So basically, we actually reduced learning rate as we have, and actually we can see our loss actually is also reduced because we have a smaller like learning rate. That means we already hit some bottleneck here. But once we hit and reduce the learning rate, I can further explore this like local and local minimums. It can really hit the point that we wanted. Okay, so that means if it's been bouncing around like this, so that means we should go down, really go down to and reduce our like learning rate that can I'm actually going down to the local minimums. Okay. So that is a very commonly used. It's just basically reduce your learning rate at like certain fixed point. Um, but you can also take certain like cosine and the cosine like scheduling. So this is another like way that we can do it. And this is basically our cosine scheduling. And it can decrease fairly slowly, but like gradually it will decrease eventually. So this is actually something called cosine scheduling. It's being proposed 6-7 years ago, which is a very popular method to train particularly large language models. So this is the initial learning rate, and this is the learning rate at epoch t, and this is number of epoch they're going to take. So that's why we are taking this and a cosine decays. So you can see this is my loss along the epochs. Can trends pretty well. So you can see so initially it decays very fast, but this is a constant and a good decays. Right. So this is a very very popular choice of cosine and the cosine decay rate. And also we have, and you can choose the linear decay. So this is also a very popular choice, has been used in the BERT, which is another like language models. Um, and also inverse squares. It's also a good one that being used. Even sometimes constant learning rate is also a good starting point to see. And also, we sometimes it's important to warm up, right? Um, so one thing is if we have very high initial learning rate, can make this loss to and explode. So what and so like I mean we take like I mean so one of the reason that will actually happen is if we take a very high learning rate and if we choose a random initial point, usually this random initial point is very far away from local minimum. So that means my gradient is very big. Then we multiply a very large learning rate. So then my gradient will like basically explode. Then my first update will overshoot. So and everything just go wild. So this is really bad. So this is a good way that to start with, we are going to do some warm up. So that means we're going to linearly increase the learning rate from 0 to the first 5,000 iterations. So that means we are actually like getting gradually going up into pretty high learning rate, then gradually decay. So this is very important that to keep in mind. Sometimes this initial part of the learning is also important. So this is called linear warm up. Um, there are a lot of like empirical rule of thumb. So that means if we do mini batches, if we increase the batch size by n, you should also scale the learning rate by n, right? So I mean to ensure this whole thing to have like very consistent results. Okay. So this is the result with and basically cosine warm up and with cosine schedules and warm up. So this is obviously a like fairly very good like training loss. Okay, what time is it? Okay, I think I still have time to talk about the test error. So how do we improve the test error? Um, so training, training is very important, but so this is say, I mean, this is training like loss. You can see this is um, like has been saturated. So this we know with a good optimization algorithm, it can reduce the training loss. But what we really care is not the training at all. What we care is the validations. If our validations goes bad, then we have a problem. So what we really care is about the error on the new data. So that means I want to reduce the gap between training and the validations here. Um, so the first thing that we should do is early stopping. So what does that mean is, I mean, even with the trainings, so you will see something like an unbiased variance trade-off, the issues that it might overfit. So that means my validation actually will getting worse, right? So so you should keep track of your validations. If you see your validation and accuracies start to decreases, that means that's the point that you should stop. So you should always early stop if you see your validation error start to decreases. So stop training the model when accuracy of validation set like decreases, or train for a very long time, but always keep track the model snapshot that works best on the validation. So that means you are going to save all these weights for each epochs, and they choose the epoch that actually give you the best validations uh, and the validation accuracies. All right, so what you can do, and we can also take some like ensemble methods. Like I mean, if you know what is the, like and boosting, so we know the random forest. You can train multiple independent neural networks, and you can and at the time test you can average their results. So like basically uh, you can average the predict probability distributions, then choose arguments. So this is basically, we have a different neural network, then we take the ensembles. Usually this will give you about 2% performances if your accuracy is fairly low. Um, okay, there are other things that we can make sure we are getting, I mean, and it can close this gap is we can add some regularizations. Um, so basically we know we can add the regularizations to this like loss functions. If we're using like SGD, adding the L2 regularization, this is equivalent as weight decay. We can also add the L1 regularization or like elastinate. That means it's both L1 and L2. Both are fine. L1 will and imposing some like certain level of sparsities. Um, okay, so what we actually can do is this is a very important techniques. Um, again, it's being proposed almost like more than 10 years. It's called dropout. So this is a very particular regularization techniques used in and the neural networks. So in each forward process, what I'm going to do is I'm going to randomly set some neurons to 0. So that means so here is fully connected here, right? So this is fully connected neurons from 4, 4, 3, 1. So what I'm going to do is for each neuron, I'm going to say, I'm going to flip half on and half off. I'm going to flip coin. If they're on, I keep this neuron on. If it's off, I'm going to turn this off. I'm going to turn off all the connections to this network and neurons, turn off all the any connections from this neuron out, right? So incoming and outgoing like connections all turned off. So this turns out to be very, very efficient. So this is basically what we are trying to do here. So we have this full process for this 3-layer neural network. I'm going to throw a random number between 0 to 1. If those things that is below than 0.5, that I'm going to drop out. And otherwise, I'm going to keep it. And so then I'm going to keep applying. And we have a second dropout mask and keep going on. Okay. So you're going to do the same thing for the backward as well. But for the forward, actually, we are adding 2 more randomness into these situations. So basically, what we do is we have 4 parses for these 3 neurons, but actually we are randomly turn off certain like any neurons with the probability of and the 0.5. So this is a probability to keep and the neuron active. The higher these values, there will be less dropout. Okay, so how can this be good idea, right? So this is a very weird way. So we just randomly turn off some neurons. So one thing is this whole thing is very important is because neural network has a lot of redundancies. And if we turn off certain neurons, so that means it forces the neural network to have some backup, some redundant like representations. So I don't want these things to overfit too much. So for example, this whole thing, for example, this this is purely and hypothetical. So if I want to distinguish cats and dogs of the image, so I would check whether it has an ear and whether it has a tail, whether it's a fluffy, and whether it has a claws, and whether it have like and mischievous look. So the whole idea is even we turn off and the three path, the remaining path can still give me a good scores. So that means this whole thing could be robust enough, right? So I really want my neural network to be trained in a very robust way. Even we turn off certain paths, I can still correctly predict the cat, right? So that means this is very important. So I want to ensure this whole thing will not overfit, that like each neuron are like basically looking the same thing. I want each neuron to looking at the different paths, so that we have some and redundant and representation. Even these things are being turned off, they can still correctly predict whether this is cat or dogs. Okay, so this is another. I mean, this is one way to interpret. Another interpretation is dropout is actually a training of very large ensembles of models that they share the parameters, because each binary mask, I mean, is a new model. So basically, like one thing, I mean, whether we turn on and turn off, this is actually new models, and we have a new set of models for each time we do the forward pass or we do like and backward passes. So this is turns out to be very helpful because, for example, a fully connected layers with 4096 unit has tons of 2 to the 4 and 2 to the 4096 of like possible of masks. So that basically essentially we're training that many models at one time. So this is even way more than the atoms in the universe. So we are actually using this kind of dropout strategy to train that many models at the same time. But the issue is, when we do testing, this might be a problem, because if we actually do testing, the dropout actually will make our output very random, right? So we have like for given some random mask, you give the images, we give our labels. But if we change our random masks, it would, so my label could be changed. So what we can do is we can try different like random masks and average out, right? But so the whole idea is we want to average out the randomness at testing time by taking the expectation. But this whole integral seems very hard to do it. You have to try different random masks again, then average out. So what we can do is we can and we can do a simple trick here. So we want to approximate this integrations very, very efficiently. So we consider one single neuron. When we do the testing, we have a probability that we have a W1 times X and of W2 times Y. So this is W1 and W2 is the probability that X and Y being on or off. Right. So then we know this will be and there will be like one so in total we'll have like 4 different situations. That means either this is on, this is off, or this is off, this is on, or both are on, or both are off. So like each of that will have 1/4 probabilities. So we're adding this 1/4 probability, adding up, we are getting 1/2 of W1X plus W2Y. Sorry, I mean the W1 and W2 are the weights, not a probability. So this is the weight of like W1 times X, W2 times Y. So these are the weights, right? So I mean, at the end, and we are getting this like in terms of expectation is just divided by 2. Okay, so that means so what we do is just we need to scale this activations with the probabilities. That would be enough, right? So basically, what we get is and if we have a P, that means we can show this expectation is just like the linear ensembles that multiply by the P. So that's why I mean, in terms of dropout, the only thing that we need is we need to multiply the p that to scale the and activation functions. So and that would be it. So that essentially calculate that the expectation automatically. So that means at the test time, all the neurons will be active always. We don't and we don't drop out in these cases. We only drop out when we do training. Okay, so that means at but in the meantime, we will scale the activation so that for each neurons, it will output at the test time that will output the expected output at the training time by doing the scaling times of p. So and we can show that this is valid and this is mathematically correct. I'm not sure. I think you don't need to implement dropout for this homework, but in 593 you probably need to do that. Okay, so this is the summary of the dropout. I think that will be I think that would be it. I don't want to get into too much today. So this is basically do dropout. So this is the dropout summary. We drop out in the trainings, but like and scale the activations accordingly at test time. So basically, essentially, we are training and the large ensemble and the models, and at the end we just scaled properly, right? So and the output will be the expected values. So if like a more common way that we do it, and some like people don't like this and the scaling. So what we can do is we can just scale during training as well. So that means when we do this dropout, we scale by and divided by p automatically, right? So and such that at the end we don't need to do any kind of scaling in the predictions. So this is more commonly used. So that means when we do the training, and we do the full process, and this whole thing will only like an effect in training. It will not affect the testing at all, because if we just look at the inferences or the testings, so this code will not confuse you, and to make sure this is correct. So this is called inverted dropout. So you basically do the dropout, but in the meantime you divide by your weight by p, right? So this is kind of you already like multiple and you like take into the considerations when we do the testings. Okay, so so this is basically the whole idea of regularization. So the whole idea is I'm going to add some kind of randomness by doing the masking of these neurons, and as like at the end I'm going to like testing all the inferences. We average out all these randomness. So of course, sometimes what we can only do is to do some and something like, and we can do is approximations, and training. And the batch normalizations. I think we're going to talk about a bit later. Dropout connect. Okay, so I think that's basic. So I don't want to talk about these dropout connect and the like label smoothing. This is more like techniques, like specific to certain problems, particularly for images. Like for example, there are a lot of things. For example, like in dropout connect, some like fractional, like and the maximum poolings, cut out the random chart. These are like specifically for the computer vision's images. But like dropout here is a very popular neural network, and the techniques for regularizations. Okay, so in practice, so these are all very important. So the whole idea in I mean regularization of the neural networks, we actually need to add random noises. And when we do the testing, we need to marginalize over the noises. So very simple ideas that like dropout. A dropout is very popular and a very important method for large fully connected layers. Okay. Okay, so we will left this hyperparameter things to the next to the next lectures.